Okay, good afternoon everyone. So today we're going to look at combinational logic, which is required in the bus communication lab, which starts next week, but also in other work that you'll be doing, including the pendulum project. So underlying all computer systems are digital logic, and in interfacing to a computer you need digital logic. So in the pendulum project, which you'll do second half semester, you have to interface sensors and actuators to a microcontroller, which is on the FPGA. And also for hardware acceleration, you employ digital logic to do that. So this is actually an important skill to have as a digital designer or embedded system designer. Indeed, a lot of new embedded processors come with some programmable FPGA logic on the chip. So there's these hybrid chips that have a hardcore processor and they have some programmable logic built in. So in the future this will be a normal thing to do, is design your own accelerators in conjunction with a processor, or a multi-core processor in fact. So if you've got a DE0 board, then they come with an FPGA that has a dual-core ARM processor on board. Okay, so we're going to look at some pretty basic stuff to start with, and I apologise if you've seen some of this, but we've got to just start at the same level. And some people may get lost a little bit through this material, but I suggest very strongly, if that's the case, you read the textbook and look at the full explanations. Please feel free to ask questions as well. Okay, so we're looking here at combinational versus sequential representations. So today we're going to focus on the combinational, which is where the output of a logic circuit depends only on the current inputs. So you change an input, the output propagates, it gets the input from and propagates that to a new output. But it cannot store any information in a combinational circuit. Sequential circuits can store information, and the output then depends on the current inputs plus the history of previous inputs. So they're storing information. So what you see here are your traditional schematic diagram for a logic circuit with gates, 2 AND gates and an OR gate. This is similar to what you're doing in the tutorial for quarters 2 at the moment. So you can represent that with a Boolean equation where y is your output, so y is equal to b and s, or a ANDed with s bar. So the inversion of s occurs here. So that's fairly clumsy, the schematic. You've probably looked at schematic diagrams and they can span multiple pages, and the hierarchy becomes difficult to read because you've got to scan up and down levels. So Verilog solves these problems by using a text-based representation for the hardware. Okay, so just remember we're talking about hardware description languages here. We're not talking about programming languages. We'll compare the two in a moment. So what we do here is we can do with a single assign statement that you see here. We're assigning y a new value based on a combination of b ANDed with s or a ANDed with not s. And that is synthesized via a compiler into the logic implementation. And that may take the form of logic gates, or it may take the form of an FPGA configuration. There is an alternative. You'll find Verilog has lots of different styles. A different way to do that is using this always block using an if statement, but we'll come back to that later. That's more complex. So a simple sequential logic circuit here shows a flip-flop with a pos-edge clock. So that's a D-type flip-flop which can store 1 bit of information. So you'll note there's a feedback loop here where Q feeds back to A exclusive ORed to form the new value of D. So each clock cycle you would update the Q output based on the exclusive OR with A and the current Q. So you can represent that in this form with a Q plus. That represents the next value of Q on the next clock edge. But you need to, of course, annotate that in your notes to understand what that means. In Verilog, we have this construction called a pos edge clock, and we'll come back to that later, but it enables us to represent sequential logic. So that's a bit of an overview. Let's proceed on and look at things from a synthesis point of view. So what's synthesis? Well, it takes some specification of logic and generates an implementation, such as a whole bunch of logic gates wired together. That's a synthesis of an expression. Or it may be a configuration file for an FPGA. All right, so what we're comparing here is a computer program. It might be a C program in a high-level language, C++, for example. You have your C compiler here, which generates machine code and optimizes that code to run on a computer or a CPU. So that compiler can target different CPU styles. It might be a IBM, PowerPC, whatever it is, and the compiler knows about the different compilation options. So that's a mapping from a computer program to an implementation. And similarly, in digital logic, we may specify a hardware description language view of a system. So then we have the analogous logic synthesis tool, which is another compiler, and it translates that high-level specification and targets a particular device or library of devices. So here we've just illustrated that with FPGA manufacturers as Xilinx, Altera or Actel. You're of course using the Altera ones. So Altera has roughly 50% of the market, Xilinx the other 50%, and then there's all these boutique companies that fit in around the edges. Yeah. So logic functions, you should all know about truth tables, I hope, and logic gates. So what we're focusing here on is the Verilog view, if you like, of those functions. So you just have to remember these symbols. So you've got the case of inversion with a tilde. You can use an exclamation mark as well, which gives you a 1-bit result. The tilde here gives you an n-bit result if it's a vector. We'll come back to that later. So the AND function is an ampersand. So again, you have this truth table, 2 1s produce a 1 output. So you can represent that with an assign statement in Verilog. And the OR function is here with a vertical bar. So to do NAND, you then combine these operators, an AND followed by an inversion, and a NOR function the same style. And finally, we have the exclusive OR function, which is a 1 when the inputs are different. So that's the same as the C syntax. And you'll notice this similarity with C programming syntax, but remember the structure is completely different with a hardware description language. We're representing hardware, not algorithms in Verilog. Okay, so a 2-to-1 multiplexer is a simple circuit we can focus on. This is a combinational logic circuit with the truth table that you see here. So let's zoom in on that. All right, so when the select line is 0, we're going to output the value of A to Y. And when the select value is 1, we're going to output the value B to Y. You'll notice these X's here are saying we don't care about what B is when we have a select of 0. So that's typical of a truth table. It's a way of compressing this 8-row truth table into just 4 rows. So in terms of the gate schematic, you can do that with 2 AND functions. You can AND when S is 0, you're going to select A via this AND term here for NA. And when S is 1, you select B, and then you OR the results together. And you can do that in Verilog with a simple expression. That's the Boolean algebra expression, and this is the symbol. So here is, let's just zoom across here. Here is the simple assign statement version using that same logic expression we developed higher up. So what you need to know here is a module, excuse me, a module statement is defining the interface to the external world with the signals on the inputs and the outputs, and there's a possibility of in-out, a double direction signal. So those signals are listed in the brackets here, and the module name is the name of the chip, if you like, that you're using or defining. In this case, it's MUX2 1, MUX2 to 1 in that definition. So A and B and S are inputs, the output is Y. So these are all single bit signals that you see listed here. So we can do that with a simple logic statement here. Or we can develop this using a structural form that you see in the middle here. So we can say, all right, we can develop a 2-to-1 multiplexer with AND gates and an OR gate. So that is directly translated with these intermediate wires, which you've defined as like local variables, but they're intermediate signals that are only available within that module, and we can assign values to those signals and then OR the result together exactly as you have in the schematic. Now that's not particularly good style. It involves low-level thinking and doesn't really respect different implementations very well, because you may not be using logic gates. You may be using other libraries with FPGAs and so on. So this form with the Boolean expression that we use here is actually more general and more applicable to different output forms. There is another possible syntax you can use with the conditional assignment statement. So you've got Y. Okay, so just zoom in on that. So there's actually a bit of confusion there, so you need to interpret this the right way. Sorry. Okay, so the way you interpret this is a conditional value dependent on S. So when S is equal to 1, we select B. When S is equal to 0, we select A. So it's very similar to the conditional in C programming. We take the result of that and assign it to Y. Okay? So this is particularly useful when you want to implement a multiplexer. Indeed, that's what we're doing. And in the first lab, you can use this syntax quite effectively to multiplex for different addresses on a bus system. Okay. Any questions on this? All right, so let's look at the issue of the difference between a high-level language and a hardware description language. So the high-level language, you might think of this as C programming, for example. So here we have various statements that you observe. So we're assigning values to A, B, and S, and then N, A, and NB. So you can then go through a sequence of instructions. You can say, okay, we know Y is NA ORed with NB, and similarly NB is defined like this. So if we look at this sequence of statements, you can see that because we start out with zeros in NA and NB, Y gets updated with 0 in those expressions. So if you reorder that in a C programming context, you actually need to compute NB and NA first if you want to represent the logic circuit, and then you do the OR of the two results and you end up with the value 1. Because S is equal to 0, so you're going to take the value A, which is 1 in this statement. Okay, so that's quite different to a hardware description language where you want these assignment statements to represent a logic form. So you've got this OR gate here represented by the first statement, and that can appear first in the sequence. Because what we're representing with this statement is this parallel functional block called an OR gate, and that lives in parallel with this computation, in parallel with the and the other bubble input AND gate that you see below. So we can write these assigned statements, as you see here, directly representing that logic, and you can do that in any order. So if I put this statement at the top, it won't make the slightest bit of difference in terms of the resultant hardware description that you actually generate. Because these operate in parallel, so there's no problem. However, this high-level language is a sequential processing. You do one statement followed by the next, followed by the next. So you've lost that idea of concurrency that's in hardware. All right, so I do not want you thinking of Verilog as a programming language. It is not a programming language at all. Okay, so let's look at some things that can go wrong in Verilog that you're used to doing in C programming. So in C programming, it's quite legitimate to assign a value to NA, then assign a new value to NA, and yet another value to NA. That's fine. It just updates that variable in memory. But if you do the same in a Verilog, so we've got an assign statement on NA, and then another one here, what you're doing is saying, okay, that signal or wire should be a result of B ANDed with S, and also we have another statement in parallel, A ANDed with not S. So that effectively synthesizes to NA being two things at once, and of course you know you're not allowed to wire the outputs of two logic gates together, because if they drive a different value you get a conflict, and you may end up with an invalid voltage in the digital system. So this is not allowed. You'll actually generate an error when you attempt to compile that. That's why we've got this here. Okay, so that's at this stage we've discussed these assign statements. These are a very simple mechanism to generate a Boolean expression driving an output. And that's the simplest way you can use Verilog. But there are limitations to that. We don't want to be writing every expression in Boolean expressions. So this is where the always block comes in. This is a way for us to express things at a higher level using if statements, for example. That's the first thing you would learn about if you're looking at always blocks. You can use case statements as well, we'll see later on, and indeed for loops as well within an always block. So an always block sits within a module. So we've got our module definition here. This is the top level description of the signals coming in and out of the MUX2 to 1 module. And internally we're going to use this signal Y that's only available within this module. So the always blocks live within a module, and you can have multiple always blocks within a module, and they represent a block of hardware. Okay, so like the assignment statement, each always block, here is one here, represents a parallel piece of hardware that talks to other hardware in parallel. All right, so the way the always block can be thought of is it's generating execution of this block when one of these signals A, B or S changes. So when we get a change in one of these signals, you then have to re-evaluate that block. Okay, so if, for example, S became 1 and it was 0 previously, you'd then look inside this block and you'd say, okay, if S is 1, Y should now take on the value B. If S is 0, of course, that corresponds to the else of this, and Y takes on A. So that corresponds with your 2-to-1 multiplexer structure. But you'll notice you've expressed that in terms that behavioural, we call this behavioural description. So you can generate some statements that make a lot of sense to you as a designer, and then it translates that later into basic Boolean expressions that can be implemented. Excuse me. Okay, so we can do this in different ways. You'll see this is the preferred way on the left, which is the higher level manner. But within an always block, we can also generate Boolean expressions if we want to do that. So that's what you see here. It's a very similar syntax to the assign statement, except you'll note there's no keyword assign in front of that symbol. And the other question I often get is, why have you got this begin end here in the always block? So an always block operates on a single statement, similar to C programming in terms of the syntax. So if you've got a single statement there, you can actually leave out the begin end and it will just operate on the next statement, the next line. But if you want to put multiple lines in there, you need to encompass that with a begin end to treat that as one compound statement. Okay, so that works fine. Here we have yet another way of implementing the 2-to-1 multiplexer. So what you'll notice here is we have this always block that triggers on any event. So that star means any change of any signal in the whole module will instigate this always block. And here we're going to evaluate NB followed by NA and combine those with the OR function. So that's similar to what we looked at in the C programming context. And you'll note now we do in fact need the begin end here to make that one compound statement. So what's interesting here is that you actually do have to respect the order in which these statements occur in the always block. Because what happens is the compiler will generate intermediate values, get to the end of the block, and that's the value that gets generated in the hardware that you're synthesizing. So the order does matter within an always block, but the order of assigned statements outside of always blocks does not matter. So as I said earlier, this always block is representing a piece of hardware defined by these statements within the always block. So that's what I just said. Order matters within an always block. It does not matter with assigned statements. So here's an example of a multiplexer structure where we've got a load, a clear, a data value, and an old value that you may have present. So what we're doing here is, if load's equal to 1, we're going to update Q with the new value of D, the data coming in. If clear's equal to 1, we're going to update Q with a value of 0. But if neither of those are asserted, then Q will get the old value. So it's just switching between values coming in. So a truth table view of that would be shown here. So if load's equal to 1, we get D here, but we get a 0 here because the clear happens after the load. So if you look at the clear, because it's the last statement, it generates the precedence rule in terms of both load and clear being 1. So load and clear are both 1, then the clear wins because it's the last statement. So when clear is 1, we guarantee the output 0. If it's not 1, then we look at the load value and we generate a D output. So that can be evaluated, if you like, or synthesized using two multiplexers. You'll note the second one is corresponding with the second statement, or the last statement, I should say, in the always block. So that generates precedence for the clear. If you have a 1 here, it's going to select this 0 regardless of what happens coming down from the other multiplexer. So if we reverse the order of these statements, As you see here now, you'll see that the load takes precedence over the clear in the second implementation. And all that happens there is we order these in the opposite order. So the second multiplexer becomes the first. Alright, so a little bit of confusion there. Within an always block, order matters. Outside in assigned statements, it doesn't matter. Alright, so this is a fairly nuanced problem that can happen, and it's called inferred latches. Alright, so I need to explain this. It's a little bit subtle. So we're trying to generate combinational logic where the output depends only on the current inputs. So if you look at this always block here, if the value of load is 0, then you note that Q does not get updated. Okay, so when load's equal to 1, we don't actually change the value of Q because there's nothing specifying what happens to the Q value. If you look at the implementation on the right, if load's equal to 0 here, we've already defined what happened to Q, so it doesn't get overwritten in the second statement here when load's equal to 0. So that means we are defining what happens to Q for all possibilities. So if you look back at the first case, when load's equal to 0, we don't want to change Q. That's what this means. So if you don't want to change a signal, you actually have to use the old value. All right? You're not changing it, you've got to respect the original value. So that means we're actually storing the value of Q somewhere in order to generate the correct output. So that corresponds to a latch. So this is a gated latch. When load's equal to 1, we're going to copy D through to Q. When load's equal to 0, we're going to remember or freeze the value of Q on the output here. So that's a storage mechanism. So what can happen is you might be a lazy or unattentive designer. Okay, and by that I mean you may forget about the case that load's equal to 0 and you want a combinational logic circuit like the guy on the right here. But if you leave out this default statement, Q equals Q old, then you will generate a latch when you didn't really mean to generate a latch. So that's called an inferred latch, and you will get a compiler warning. So some people want a latch, so we can't just say that's an error, but just be warned that sometimes you may miss different paths through your logic in an always block so that you generate latches because you haven't specified what happens to the output for some input combinations. And yeah, we can come back to that point later because it is fairly technical. Alright, so let's move on and talk about multi-bit and bus notation. So we're going to look at buses, so this is obviously relevant. So up to now we've discussed single-bit signals, so every signal is just representing one bit of information. But as you know, when you start doing arithmetic or deal with information in sort of byte form or word form in a computer, you have multiple bits to deal with. So you need to represent that with an array of bits, which is what happens in Verilog. So you'll notice here, this statement here, we've got the input bracket 3 colon 0 A comma B. So this 3 colon 0 is representing bits 3, 2, 1 and 0. So there's 4 bits represented by that array. And similarly with B, it's an array of 4 bits. So that's just declaring a signal which is a vector, which is a 4-bit signal. And similarly with the output here, we have a 4-bit Y output. So we can now deal with these as if they're just normal signals, but you need to respect the fact that we have multiple bits available. All right, let's look at the example on the right-hand side first because it's a bit simpler to understand. Just ignore the green stuff for the moment. We'll come back to that. So what we have here is an expression for y. So we're trying to implement a multiplexer which is 2 to 1. So we want to select one of two 4-bit inputs and drive the output with that selected 4-bit input. So the S value, it's a single bit, can be 0 or 1. When it's equal to 0, we want to select A and drive that through to the output. So that's what this expression here does. When S is equal to 0, we have a 1 on S bar. We AND that with A. Remember, A is a 4-bit value. And this term here will be all zeros, so you OR the result, you get the required output. Okay. Unfortunately, the textbook made a bit of a mistake here, which is a little bit bad, but we can fix it pretty easily. So what happens when you AND A, we'll do the B one. If you AND B with S, when S is 1 bit and B is 4 bits. So what does Verilog do? Well, it generates, unfortunately, it will generate a 1-bit result. So that 1-bit result is generated by matching up the bits that it can from the least significant bit upwards. So in our case, we have S as 1 bit, so it's going to match that 1 bit with the least significant bit of the B value. So the result of that would be the same as B0 ANDed with S. Okay, so that's what Verilog does. It allows you to mismatch things in an AND function quite silently and generate this 1-bit result when you actually expect a 4-bit result. So to fix that, we need to change S to be a 4-bit value that replicates each bit the same. Alright, so that's what we've got here actually. But this new signal called S 4 bits. And we've defined that as a 4-bit wire. And we've made that equal to 4 copies of S concatenated into a 4-bit vector. So that's a bit hard to swallow, but we'll look at concatenation in more detail in a moment. But the curly brackets are a concatenation operator, and you can replicate bits in this form. All right. So for the moment, you can just say that's a 4-bit vector, and now we can AND that successfully and generate the correct result. Okay, so the other thing that you see here is important. This is the concept of taking a copy of another module and creating a copy within the current module. So if you define a design and you want to build up a hierarchical structure where you want to reuse your earlier modules, you need to make a copy of those in your current module, and you can do that 4 times as we do here and generate a 4-bit version. So that process is called generating an instance of another module, or it's called instantiation. So instantiation is a way to generate multiple copies of other modules you've already defined, and that's the case with us. We've defined this module called MUX 2 to 1. So that does single-bit multiplexing of inputs to generate output. So then you need to work out what you connect up to the inputs and output of that module. So that's what's happening here. It's a little bit, looks messy, but it's actually quite systematic. So we take the A input of our 2 to 1 multiplexer. We're going to connect that up with the brackets to the value A brackets 3. So this A brackets 3 is the most significant bit of the 4-bit A vector, and we're going to connect that to the A port or the A input of our 2 to 1 multiplexer. Similar with B, and we're going to take that result and generate S, that's a 1-bit input, and the result here is the high-level output bit. And we do that 4 times. So that's just taking 4 copies and instantiating that. So in the lab, you're going to have to learn how to instantiate other modules. This is how you do it. There is another way to do it, which is just based on the order of the signals only without labelling them with the port, but I prefer you to use this method because it's much more robust and explicit with what you're connecting. Alright, so let's look at other variants. It is interesting to do that because we can use always blocks to do this as well. So we want our 4-bit 4-to-1 multiplexer now implemented in different forms. Okay, so this is a 4-bit 4-to-1 multiplexer, not 2-to-1 multiplexer. Okay, so let's just look at what we're trying to do here. We have a select line now which is composed of 2 bits because we need to select 0 to 3, which is 4 possibilities, so you do that with 2 bits. So the 0, 0 case will select A through to the output Y, and the 1, 1 case will select D through to the Y output. And all of them are 4 bits. So the way that we can do this with our existing knowledge is using if statements in this always block here. So these port definitions you should be able to understand. We have an internal signal which is called Y, and the use of this reg here, you might ask, why don't you declare that as a wire? Well, it turns out in Verilog, whenever you use a signal within an always block, you must declare it as a reg type. Okay, sounds a bit odd, but it's for historical reasons. I would prefer if they just called it a wire and worked out where it resides, and so be it, but you'll get an error if you call it a wire. So here we just check S now. Is it equal to 0, 0, then output Y equal to A? Otherwise, we check it against 0, 1 or 1, 0 and put out the corresponding outputs. So this is the equality operator. It's just similar to what you see in C syntax. All right, so that's quite messy. A much cleaner way to do this is using a case statement. And this is the recommended approach to implementing multiplexers. Multi-bit select of multiplexers. So the case statement is a case on the select 2-bit value, and these are the values it checks against. So S can be 0, 0, 0, 1, 1, 0, or 1, 1, which is the default in this case. And then you're outputting the corresponding values. So when you go into Quartus, you can look up the syntax for these things. I know it's a bit overwhelming looking at it in these examples, but you can then say I want a multiplexer, and it gives you a template set of syntax you can then edit in the editor. So that's what I'd recommend you do, because you've got to remember the end case, the default, and putting in the switch inside the brackets, all that stuff. All right, so moving on now to addition and subtraction. So while we do this, what we actually, just a point I should make is, in these notes they show you different forms of implementing, say, multiplexers and adders and subtractors and so on. So what you should be using in practice is the high-level form, which is usually the last possibility. So when you're designing, you should be using the highest level form of this construction or the hardware description. These are alternate lower level forms that are not recommended to be used in practice. So similarly with addition and subtraction, we're going to start off with low level implementations that you will see are not very nice, and we'll then move on to how we do it in practice. So if you look at addition of A plus B plus carry in, this is a full adder. you get a 2-bit result of the sum and the carry out. So binary addition you should all be able to do. It's simple carry of 1 when you get a result of 2 or more. So that carry out then feeds to the next stage. So we have our full adder here. We're adding the low order bits. We carry out and add that to the next order bits and so on. So that's a ripple carry adder that you should have seen in your earlier work, and you can represent that with a multi-bit version that you see at the bottom. So in terms of the full adder, you could do that with a truth table as we did here, or exclusive OR functions, A exclusive OR B, ORed with A with CI, or ORed with B with CI as the carry out, and the sum is just exclusive OR of all the input bits. So that's all very nice. So we can now implement that in several ways. And what you see here is the simple form on the left. We've got our 4-bit inputs and output S. We just write that as A plus B. So the result of A plus B in Verilog, we're adding 4 bits to 4 bits, is a 5-bit result. Okay, because you get this carry generated that's the possibility of the carry out is not ignored in Verilog. But you'll notice here we're assigning that to a 4-bit S value. So what happens to the carry out? Someone tell me in this example. It gets neglected, yes. It gets thrown away. So this 5-bit result, when you do the assignment in Verilog, it takes the least significant bits and stacks them up and produces the S value, and then it runs out of bits, so it just throws that away. However, you will get a warning message. You'll get a warning message when you compile this that bit number 4 of the result is ignored, something like that. All right, so here we're actually doing this more rigorously on the right-hand side. So a 5-bit sum is the result of the A plus B that we just discussed, but we're going to store the carry out in this example. Okay, so what we're doing, it looks quite clumsy here because what we have to do is we need to do 5-bit adds with 0 in the top bit, because if we did this any other way, then the carry would get ignored, because when you add 3 things together, you need to be mindful of the bits propagating through to the output. So what we've constructed here is a 5-bit value of A with a 0 on the most significant bit, same with B, and CI is the carry in. We need to add 4 bits because it's a 1-bit value. So we're adding 3 5-bit values and assigning that to Y. Now, because we know the top bits are 0 in the first 2 cases, you know that can't actually overflow into 6 bits. So you then get the 4-bit result, and the carry out is the 5th bit of Y. Okay. So again, you see this concatenation operator. So to construct a vector of bits from individual components, you need to concatenate multi-bits. So just another word is, you've noticed this weird syntax here for a 4-bit value of 0. So let's have a quick look at that. So the 4 represents the number of bits in the constant. We're talking about a constant here. So 4 dash says, okay, we've got 4 bits, and we're going to represent that in binary. So you write a B, and then you write 0, which is then converted to 0, 0, 0, 0, 4 bits. So we could have written that differently. We could have written this as 4D0 for decimal, and you can use octal as well, and hexadecimal and other radix values. But the convention is when you're dealing with bit level, you stick to binary or hexadecimal, because it translates directly into the format. So the advice is you should use decimal when you have large numbers and you don't want to do the conversion into binary manually because you'll make a mistake. So you use decimal wherever possible, but binary for bit level manipulations. What about subtraction? This starts getting into the territory of 2's complement representation, which a lot of you will have forgotten, I think. So let's just quickly revise that. If you have a number, it might be so we might stick to 4-bit 2's complement to start with. So 4-bit 2's complement representation can represent numbers from minus something up to plus something. Does anyone know what that is? What number range can we represent with a 4-bit 2's complement representation? Quick revision. Minus 7 to plus 7. Does everyone agree with that? Because it's wrong. It's close, but it's not quite right. I agree with the plus 7, but I don't agree with the minus 7. Minus 8, yes, very good. So if you look at the binary representation of that, minus 8, it turns out to be 1, 0, 0, 0. Plus 7 is 0, 1, 1, 1. And you're actually using, and if you look at 0 in the middle, you're using all possible 16 combinations of those 4-bit values. Okay, so 2's complement is not symmetric in terms of the representation. First thing is the most significant bit is the sign bit, so that works well. So a 1 represents a negative number and a 0 represents a positive number. But if you do have a negative number, say minus k, how do you represent that in 2's complement? How do you generate the bit pattern for that? Can you do that in a mathematical form? What you've described is a structural implementation. What's the actual mathematical form for that? No, no. Go up a level. No, you're still thinking of the bit level. Yeah, so you actually do complement the bits and add 1, but where does that come from? Why is that true? So you represent this in practice for a 4-bit representation as 2 to the 4 minus k. Okay, that's where this comes from. So that would be 16 minus k. So if we're looking at minus 8, you take 16, you subtract 8, and you get the number 8, which is this bit pattern 1, 0, 0, 0. So you may wonder, well, how does this all work? Well, if you take 2 to the 4 minus 1 minus k and add 1, that's pretty good, isn't it? It's the same thing. But 2 to the 4 minus 1 is the bit pattern 15, which is 1, 1, 1, 1. And if you subtract k from something of all 1s, then you end up with k bar. How does that work? Well, let's just do an example. 0, 1, 0, 1. Subtract that from all 1s, so 1 from 1 gives 0, 0 from 1 gives 1, and so on. So you'll notice the bit pattern is reversed. So that's the bitwise complement. So yes, you do take the bitwise complement and then add 1. That generates the 2's complement because you're actually using this expression here. So the reason I say this is because when you have 2 to the 4 minus k and you add that to a positive number, so let's just do that. We add it to n where n is greater than 0. Then you're generating n minus k plus 2 to the 4. So n minus k plus 2 to the 4 in 4-bit representation is just n minus k, because 2 to the 4 is 1 with 4 zeros over after it, so that's a 5-bit number, so we throw that bit away. So that's how the 2's complement actually works in practice. It generates subtraction automatically out of addition. So this is what you see here in this implementation here. It's just generating that for you. But the good news is that Verilog does all of this for you. Okay, so you can write this as just A minus B as you see here. Okay, so A minus B will do the bitwise complement, add 1 and then do the addition in terms of the hardware for you, but you can work with the operator of addition and subtraction directly. And by the way, don't use plus thinking it's an OR, it's actually an addition in an arithmetic sense. We better stop there, and I will proceed on next week with introducing the bus communication lab. We've got enough Verilog here, but please read the textbook by Reese on Verilog to fill in the gaps. Everyone's going to have their questions about this stuff. You don't have the full context just from a lecture, so read the textbook and fill in your gaps. All right. Thank you. We'll finish there. Cheers. See you around. Yes.
Yes, in one of your slides, there was this place in the 2-to-1 multiplexer where you had the load taking precedence over clear.
Yes.
And you said that that logic is minimal and you put it in the brackets. What did you mean when you said the logic was minimal? The logic is not minimal is what was written when load took precedence over clear. And in the second part, when clear took precedence over load, it was just like...
So when the logic being minimum is a result of the compiler operating on the Verilog.
Okay.
So the compiler minimises the logic.
Okay.
But you can express it in a way that doesn't appear minimal, but it gets minimised later on in the compiler. So what you had in the case in the always block, you had 3 statements. So you might think that's not minimal, but the compilation of that still can be minimal. All right, so don't get confused with the 2 minimal versus